I'm Dierk Ohlerich, I'm Chaos from Farbrausch, and I'm talking a little bit about compilers and assemblers and optimizing code without writing too many assembler instructions. Komm schon. Tada. Yeah, I'm a little bit sorry that I don't have made cool slides and stuff, but I was too busy enjoying the party here, Breakpoint 2005, and I thought it was a little bit more important to be at competitions, be outside, and seeing the concert yesterday than to make cool slides out of all this text. So I just go through this HTML file here. Anyway, the compiler is the most important tool for every programmer, and the better you can use the compiler, the better your code will be. Actually, there are three compilers which are commonly used. That's the Microsoft C compiler, the Intel compiler, and the GNU compiler. They are all extraordinarily good. Everything I tell here is valid for all three compilers, although the little details may be varying. The main difference is, of course, with the GNU C you have the greatest platform independence. For instance, I'm using it for PlayStation coding a lot. With the Intel C, you definitely get the best speed of the compiled output. It is a little bit better than all the other compilers. And the Microsoft C is the most useful all-round tool, I think. Not only because of the user interfaces they made. All the other small compiler options are pretty good, especially if you're doing intros and stuff. There's another thing, Microsoft is the most expensive compiler. The Intel C is even more expensive, but at least it's free for Linux and uncommercial use. And the GNU C is, of course, completely free, so you can do demos with it without being illegal copying software pirate. Anyway, everything I'm telling you will be Microsoft C++ specific, but it should be easy to adapt it to the other compilers. And actually, I have adapted it to the other compilers in some parts. There are two other tools that you can't get without. The first is Intel Vtune. This is your best optimization tool you can ever find. If you do not use it, unfortunately it is not free, it is extraordinarily expensive. There's a 30 days trial version, which they will flood you with emails when you go through the registration. But if you're working in a company, make your boss get the software, and then you have the ability to use it for your own software as well. Another thing which is extraordinarily useful is the NetWrite assembler, NASM. I try to avoid writing large pieces of assembler, but when I really have to, and actually I haven't in the last 4 or 5 years. Anyway, when assembler, then this is the best assembler because it doesn't use a strange Intel syntax. So these are basically the tools you will be using when you're programming. You will be spending most of your time, of course, with the text editor, but much of your productivity is how good you can use your compiler. We will be talking most about optimization, and before we can talk about optimization, we must mind the rules. And the first rule of optimization is that you must know what's going on, and that is about measuring. If you do not measure, if you do not time your code, if you just start optimizing what you think might be a bottleneck, then you're wasting your time. Most of the times your bottleneck is not where you expect it, especially if you have already done the basic optimizations. So measurement is the first thing you have to do whenever you try to optimize something. The other thing which is important, once you know which part of your program sucks, you have to know what's going on. Otherwise you can't change it. You can of course hack a little bit around, but it's a lot better to know what you're doing if you want to be good. And the third rule is actually the first rule. Premature optimization is the root of all evils. Don't start just optimize around everywhere. Do the optimization only based on measurement and on knowing what's going on, knowing how to do things better. Otherwise, you're again wasting your time. And the best way to find out what's going on is using Intel Vtune. It's very simple. You start your program with Vtune running in the background, play around a bit with it, let's say 30 seconds, 1 minute, and he will do one sample per millisecond. This is the easiest mode of Vtune. And every millisecond it will find out where the stack pointer, where the instruction pointer is. No matter if the computer is spending its time in the driver, or if it's spending in your code, or if it's a Winamp which is running in the background all the time, it will get all the stuff. And then it will tell you where the performance went. It will tell you that you spend 3% of your time with the Winamp which is running in the background. It will tell you that it's spending 50% of the time in the driver because you made 2 small batches. And it will tell you that you have one routine which is the bottleneck of everything you did. And then you can start optimizing the one routine which he might find out. And it is often not the routine you expect, the one routine which is your bottleneck. And so it goes on. You optimize the function that Vtune found, and then run it again. And if you did a good job, this old bottleneck will go away, and you'll find another option which is the worst one. And then you start optimizing on that one. Another good way of finding out what's going on is live performance metering. For instance, in our programs, we have a simple instrumentation which looks like this. We have this macro which generates an object and destructs the object when it gets out of scope. And all this object does in the constructor and destructor is setting some timing variables. And we put it everywhere in our code, this little macro. And there's another program which gathers all the information and makes a little bar what's going on. When I was programming on the Amiga, I always was changing the background color of the screen. And then I had stripes going on the screen, and I made little marker on the screen so that I knew, well, I have to optimize 4 more centimeters or raster lines. This is not practical today, but I still like this real-time display of what's going on in my code. Actually, I can show you how it looks if you're using it in the Werkzeug. I hope this works. Release build, F5. Okay, no, lieber nicht. For instance, this is the Werkzeug. I'm switching to low texture quality because I don't want to wait through all the pre-rendering. And now it's calculating all the textures. This takes a little bit, even with low texture quality. Everything is a little bit slower in the Werkzeug because there's a lot more going on. Yeah, well, that was 57 monsters dying because they were placed outside the world. But you see, this is our performance meter. I had shown you that material setup is a routine, and now I see that he's spending 100 whatevers microseconds with material setup, which is pretty good. And this long red bar is waiting for the graphics card. And if everything works as it should, they just died again, you know. I can go here and I can see how everything I don't want the sound anyway. So I just can see how the performance changes depending on what direction I look. This is after all the optimizations Rück did, and therefore you won't see any big performance problems because they have all been solved. But I can also check how it happens if I switch off the lights, how it all changes the different things we do here in our 3D engine, or disable the shadows. Then I will of course have no shadow volume extrusion, which makes things faster. I think this is, and I always can see the parallelism between graphics card and CPU here, which is at the moment no problem. Yes, so much about, we have no mem leak. Very good. With simple methods like this, you can get a real-time preview of what's going on your program. You see, with Vtune, you only see an average over the whole program flow. That might be not enough. But with this, you can peek into your code and see directly what's happening, when it's happening. For instance, we found out that in certain times, Krieger went totally slow, and we saw one bar, which was the collision detection, rising and rising and rising, and then we knew, okay, it's a collision. Some monster went somewhere where it shouldn't have went. Another thing about what's going on is Crunchy. Crunchy is the packer Rick wrote, and actually at the moment most big 64K intro groups have access to these packers and they love it. And there are two reasons. The first reason why they love it is it has a very good pack ratio. But the second reason is, and maybe even the more important, it gives this output. It tells you how long a function is before compression and how large it is after compression. When you try to size optimize code, you often make some changes and see if the executable went larger or smaller. But you have to consider that you always have to check the size after packing, because some straightforward code which has a lot of repetition might pack a lot better than a small piece of code that has no repetition. So always check the compressed size of your code when you're trying to optimize an intro for size. And with Crunchy, you can get this dump which tells you which function took how many bytes. And this is a real power. You can see, well, this is the demo build, so all the unoptimized routines from the OGG players take most of the size. The largest operator, which is still there, is the walk operator, which actually makes the leg movement. And well, unfortunately, there's really a lot of stuff in there, so we can't really optimize it away, because then we would optimize away functionality. So it is worth spending a lot of time into measurement methods, because you will get this time back in increased productivity, and this is something you really should care about. Another thing is, does anybody here in the audience still write whole programs in assembly language? Do you have any good reason for doing that? Like it's a PlayStation or it's a C64. That is an extraordinary good reason. Well, because without a flat memory model. Anyway, so I think on PC nobody really does it anymore. And while assembler gives you the best possible performance if you are a really cool programmer, compilers are much more productive. And actually most people write worse assembler than compilers. Even if they think they're smart, they can't be all the time smart. So, and the worst thing is that assembler loses flexibility. If you have written something in assembler, you can't change it anymore. And that is awfully bad. But before we can consider writing something in assembler, we have to see what a modern CPU does. And this is totally different from what's happening inside a C64, because 2 or 3 instructions are fetched simultaneously. They're totally ordered, dependent sorted. It can take hundreds of cycles from fetching an instruction to retiring an instruction where it is finalized. And so it's totally waste of time just to count clock cycles. Well, I think I can skip this. I must skip whole chapters of this talk because I don't have the time to talk about everything. And although it is pretty much useless to write large pieces of assembly directly, it is very useful to read assembler, to look at the output of the compiler and see what's in there. For instance, I once wrote this piece of code. It's just some kind of landscape engine which dumps lots of polygons into a vertex buffer. You see, this is a vertex buffer pointer, and he writes 4 values in it. And well, this loop shouldn't be much of a problem. The calculations are awfully simple. It should be mostly bandwidth limited. So with a loop like this, I would expect that I get full AGP bandwidth. but I didn't. It was too slow. I measured the performance and I found out it should be twice as fast, considering the AGP bandwidth on my computer. What was happening? The compiler was an extraordinarily smart piece of software, and it had changed, for reasons I don't understand, this store with this store. So it was first storing the 0, then the 1, then the 3, and then the 2. And this is a very bad thing with AGP memory. AGP memory works best with sequential writes. And by no means you may leave holes. You must always write every byte of a vertex buffer when it goes directly to AGP memory. Because if you don't, the CPU will not be able just to flush out the bytes from memory. It will read from the memory the whole cache line and change to get this one hole you had. So what did I do to fix it? I could have rewrote this loop in assembly to get the order right, but fortunately there's a volatile key statement. Where am I? Here am I. This statement tells the compiler to not change the order of memory access. And, well, I just write one line, the compiler completely rewrites the loop. It is, I think, the same number of instructions than before, but it obeys the fact that it has to write in sequence, in the same sequence that I wrote. By just making this variable volatile, the loop got the perfect performance. It was as fast as AGP memory allowed it. And what happened? I looked in this assembly. I found out what the compiler did. I made the compiler to write the code I want. I didn't write it myself. I forced the compiler, and I got the perfect performance. That's what I want. Again, write in sequential order when you're writing vertex buffers, and write every byte. This is even more important. Writing every byte is the most important rule when dealing with AGP memory. Don't think that you can save memory bandwidth by leaving a hole in your writes. Yeah, the fact is that I've already said it, and the compiler writes better assembly code in milliseconds than you can write in hours. Most of the time, when you think about optimization, you must know about the caches, because the CPUs are fast, but memory access isn't. So as long as you are running in first level cache, you are fine, no problem. When your data grows above 16 kilobytes or 32, then you are running from second level cache. That's okay. But once you are running on main memory, you really have to care about your memory accesses, about streaming, about all this stuff. Because most of the time your performance is not in the calculation. You lose your time waiting for memory. And this is actually the same no matter what language you are using. So now let's go to the C++ compiler. We want to use it as a tool that generates the code we want it to. So we have to know what happens when we are using all this fancy OP stuff and all these cool tricks that came up in the 90s. There are a lot of features modern programming languages just have. But what's really happening? For example, single inheritance. What's happening with single inheritance? Well, it's as simple as you would expect it. If you inherit a structure, the new members are just added at the end. So if you use it, it doesn't matter. There's no performance loss of any kind when using inheritance. It just works. With multiple inheritance, it's a real mess. You should, if it is a performance critical application, you should be knowing what's going on. There's a reason why modern languages don't feature multiple inheritance. There just ain't a good implementation for it. Constructors and destructors are also a very simple thing. It's just a function that gets called every time you create or destroy an object. As long as these functions are inline, well, the functionality in there has to be done anyway, so it's no loss. If they are large, then your objects are complex, and then it's no performance. Well, complicated things take a lot of time, and so it's no problem. But there's one special problem about constructors you should be aware. When you have a very small variable structure like a 3D vector, x, y, z, w, or something, or RGBA, and you make a constructor for it, and you then create an array of this object, the compiler will call the constructor for every element of that array in a loop. So when you have something like a vertex which contains of 3 vectors, and each vector has a constructor, and then you're creating 10,000 vertices, then there will be some loops generated which call 30,000 constructors. This is something you might notice. So I actually tried to add a constructor to our vector class, or XYZW 3D vector, and the code size rose by 1 kilobyte. It's not only the code size, it is code which gets executed without doing anything. So you should really consider if small structures really need a constructor or destructor. And I have my own style guide. If I say struct, then there's no constructor, there's no destructor, there's no virtual function, it's just that, a struct. But if it's called a class, then I use all those fancy features. So that I always know this is a small thing, don't do something strange with it, and this is a large thing, it has all this whistles and bells. Another important thing is new and delete. Unfortunately, they're very, very slow. And unfortunately, you just need dynamic memory. Maybe except for the C64, where you just know where everything is. So we can't do much about it, but we should remember that they're expensive, and don't write something like that where we are creating objects all the time. This is just a stress test for the memory manager. It might be optimized for it, but well, why do something like this? Another thing is, if you allocate a large amount of memory, like for our texture generator, we have lots of bitmaps that get allocated dynamically. It's a bad idea just to clear it right away, because then you're wasting memory bandwidth. You're writing the memory once for clearing it, and then you're writing it again with some useful data. And this might make things twice as fast. This is one reason why debug builds are so slow. For instance, D3D debug is awfully slow sometimes. And when you then use Vtune to try out what's he doing, then you find him sitting in a mem clear routine, which clears all the render targets and stuff you allocate. So not a good idea to have it on all the time when you're watching demos for fun. And well, actually, this cache problem is the reason why the operating system doesn't clear the memory by itself. It's just too wasteful. Memory management can be a huge performance gain. This is your chance to be smart. But sloppy memory management is the main reason why the programs we use are getting slower and slower. But unfortunately, it's also the major reason why programmer productivity rises. So you just make your balance here. How much garbage collection or whatever you want to use to do your memory management. Java programmers don't have a choice. They always have to do the improved programmers' productivity. They will never get the performance optimization possibilities. Another thing which you can do with object-oriented programming are virtual functions. This is basically a function. Every time you call a function, he looks in a jump table. What's he doing in that function? And the overhead is one pointer per object, per pointer to the function table, and one assembly instruction per function call. That won't hurt. That is no problem using virtual function. Actually, unless you make every function virtual, the alternative to a virtual function call would be a switch statement. And that's larger, it's slower, and it's a mess. So virtual functions, not only from the design, it's a good thing, also from the performance point of view, it's a very good thing to use. Don't fear virtual functions. Exceptions are, well, the common knowledge is that exceptions don't cost anything when you don't raise them. Only when you raise them, they can be pretty expensive. And the reality is that exceptions cost something, even when not used, but not much. But when you use them, it's awfully slow. Slower than you can imagine, because it is an exception. When you enable exception handling in Microsoft Visual C, you will get this additional code for every function call. When you have lots of small functions, this can be a real problem. You get other problems just by enabling exception handling. This really makes me shiver. I haven't seen any segment registers for years. They really use some strange text. Actually, I think this is the reason why the AMD 64 technology still uses this FS register. I don't see why they would use it anyway. There will be additional overhead for cleaning up objects. There will be lots of tables generated for exception handling, and actually lots of optimization opportunities, because every function might fail, and the code generator just can't keep things in registers, because, well, the function might fail and there might be a jump across the whole program, and it must prepare for that. So what I think, don't use exceptions for intros. Krieger gets 4 kilobyte larger just by enabling it, without using anything. No, doing a press of the button in the compiler options. And but for your inner loops, it shouldn't be a speed problem, because you don't have function calls and stuff in inner loops. And if you have, well, that would be your first thing to fix. Templates, another very new feature. It's well, great to show off how your evil hacking skills. You can do the strangest thing with templates, even worse things than you could do with define. But there are also very good uses, like type-safe containers, or like a swap function or a mean and max. You can use templates a lot. Well, what template actually does, it duplicates code. And when you're optimizing for size, duplicating code is a bad thing. Even when you're not optimizing for size, duplicating code is a bad thing, because you will always want to stay in the instruction cache. The instruction cache is very small, 16 kilobytes. If your code grows larger than 16 kilobytes and you jump around a lot, it will get slower because of instruction cache misses. So you have to use templates wisely. It can be very bad for intros. For small functions, it is not bad, because the stuff gets inlined and, well, no loss at all. For larger functions, there's a simple trick. We have this as a dynamic array class in our code, in our intro code, and we actually inlined everything, but the really nasty things, where something real happens, there we have a function call to a non-templated class. So that the template itself only generates inline code and jumps off to the other class when the inline code would be too large. The result is that I have no code duplication, that I have maximum performance because the critical routines are inline, and yeah, I can really use this in intros. Let's think about a class where we only store pointers, like some kind of object list or so. So we would have templates. The compiler would generate code for every different class, although all the codes are absolutely identical. All pointers are 4 byte. So the compiler should be able to merge it, because the compiler generates a copy for each function. The code for each instance should be exactly the same, since the array of pointers is not interested in what the pointer points to. The linker should find out that the functions are identical and then merge them. Well, I don't believe it. But what actually happens, I wrote this program. This is a very complicated way of finding out the size of a function. If of a variable, I had to write it because otherwise the compiler would just optimize everything away. So I came up with this. The compiler is not smart enough to optimize this away, so he actually generates the code for this. And then I generate 3 test cases, one int, which should result in 4 bytes, one float, which is 4 bytes, and one double, which is 8 bytes. So he generates this code 3 times to compute 4, 4, and 8. And what does the linker? He finds out that the first 2 instances are exactly the same and puts them on the same address with a different symbol, but on the same address because it's the same. And the third instance is different because it generates an 8 and not a 4. Perfect. We can use the templated array to pointer without any precautions. Of course, we have to check from time to time if everything is right, but it just works. Another thing you can do with template is metaprogramming. I'm not going into the details here. I don't like it a lot. Mainly because this is a very smart programming trick, and debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. So don't be too clever in the stuff you do. The first problem is you might not be able to debug it. You might not be able to understand it months later. And the worst thing, the compiler might not be able to debug it, to analyze it correctly. Sometimes optimizations, which by theory should be no problem, just don't happen. You have this 10 kilobytes of template instantiation stuff, and it should evaluate to 1, but maybe it just generates code worth of 10 kilobytes for evaluating it. So you always have to check if the compiler is as smart as you believe. And most of the times it is as smart. Most of the time it's smarter than you think, but sometimes it isn't, and then you have to check. Therefore, you have to check. And Vtune again is a very, very great help for it, because if something really goes wrong and it is important, Vtune will show you. Vtune will show you a function where 10% of the performance are spent, which should be nothing. Look in it, you see lots of assembly code for nothing, then you know, oh shit, the compiler fucked up. Have to do about it. The next topic is, sometimes the compiler does bad code and we have to trick him into doing the right code, and sometimes we really have to write assembly language. 3 ways of assembly languages: separate assembler file with nothing, last resort. Usually we don't have to do it. Inline assembly, just have a few assembly instructions inside your code. Good thing, or the best thing, if you can make it run intrinsics. The compiler automatically merges your assembly to the C flow. Inline assembly often usually looks like this. You have a few functions which you can't do in C. This particular macro does not compute A times B by C. The intermediate result is 64-bit. You can't get this code without any tricks. Actually, I saw GNU-C doing this kind of code once on a MIPS processor, but I haven't seen Microsoft compiler generating it automatically. A very, very useful thing. Another thing you could do is you want to access the ZenCost function, then you can just make some inline assembly. And here you see this is a little bit of a mess because this is not perfectly merged with your own code. There are some moves which might not get optimized away. It's a good thing, but we need something better. Another typical example is something like this, where you just want to do some MMX code in the middle of your code. This is where we use inline assembly most of the time. So the bad thing about inline assembly is that it doesn't integrate seamlessly between C and assembly. Another thing is that you're still writing assembler, and assembler is not so productive. So there's a better solution: intrinsics. With intrinsics, you just write the assembler commands as if there were C functions. And then the compiler automatically inserts the instructions, manages the register allocation. You don't have to care about registers. You don't have to care if you run it out of registers. The compiler will just put the instructions where they belong and spill the registers if that is necessary. I think this is very hard to read, but it's a lot easier to write than assembly language. So it's basically a good thing. You don't have to do register allocation. The integration is seamlessly, but you have to check the code. Sometimes the compiler runs out of registers, and then he just makes load store, load store, load store. This happens a lot more with Microsoft than with Intel compiler. So you have to check if everything went right. It is actually sometimes not as smart as you are. What do we have here? Yeah. I want to skip all the standard intro coding stuff and go back to the intrinsics. When you're coding an intro, you're not linking the standard library, so you're missing important functions like sinus and cosinus. But of course, for these instructions, they're intrinsic also. You just write something like this, declaring the function and using the intrinsic pragma, and then the compiler knows about whenever you write Zine, it just makes the assembler instruction for Zinus. You don't have to link the standard library. You don't even need the mask.har header. Well, is it working? I wrote a little test program which uses the memset and stringlang built-in versions. And it actually works pretty good. For instance, the stringlang doesn't appear anywhere. It just counts the string and writes directly the 12 into the code. The first memset was translated into a rep loop, and the second, which is 8 bytes big, was 2 moves, because that's better, that's faster. So the code that we just generated is really cool. Of course, one could know that these arrays are directly after each other and just make one loop, but well, the compiler isn't that heavy. This more thing you have to do to get intros right, but I don't have the time for it. I just want to stay with this check stack function, because it's doing some pretty interesting stuff. Whenever you try to link without standard library, you might have found this check stack functions. Whenever a function needs more than 4 kilobytes on the stack, the compiler will enter this function into your code. And the best way to get rid of it is just don't have stack frames larger than 4 kilobytes. This is most likely that you have a large array on your stack, and then make it static, then it won't be on the stack, and the function is away. But what's happening there? What is it doing? Windows stacks grow in virtual memory. If you touch a page on the stack that is not already in physical memory, Windows will grow the stack accordingly. But this autogrow feature only works for the next page. So if you're randomly accessing on the stack not the next page but the next page, then it will just be a page fault. And so whenever the stack frame is larger than 4 kilobytes, this function is called, which does one memory read all 4 kilobytes, so that Windows operating system can grow the stack for you. This is what's happening inside. Another thing that you have to write yourself is F2L. F2L is a very small function which does nothing but converting a float into an integer. Unfortunately, this is a very slow and large piece of code. And this is actually because the rounding modes which are defined by standard C are not the ones which are used in the floating point unit. So it has to change the floating point running mode, do the conversion and change it back, and that has to flush the whole floating point pipeline, and it is awfully slow. If you don't care about accuracy, you can just write something like this. Use it instead. It's not standard conform, but a lot faster. And actually, this is your trick to do a 5% performance improvement on most programs. When you start Vtune, you usually see F2L somewhere taking 5% of your performance because you didn't care. If you care, it's just gone for free. If you can live with the unprecise rounding. Now we have 5 minutes left. I think we go directly to the shader compiler we wrote. Willst du? You cannot only use compilers. Compiler building is a lot of fun. I actually pick every opportunity to build a small toy compiler. We actually wrote 6 small toy compilers for the Kia project, which do different kinds of scripting languages, format conversions, everything. These are of course not fully bloated up compilers. These are just small things, tools for us. But still, they saved a lot of work. And he's now talking about our latest invention in generating shaders on the fly.
Okay. Yeah, I'll have to find the place. Yeah. Okay. The basic problem is in Krieger we have a lot of different shader types with different texture layers and so on, different texture coordination forms. So this is a lot of shader permutations we have to manage, and you basically don't want to have hard-coded shaders for every variant, especially because most of these variants only differ in 1 or 2 instructions. So we want a method to generate these slightly differing permutations on the fly. Originally we had a shader compiler that just used the Direct3DX shader assembler and generated text code for the shaders we had, which was basically a lot of sprintf and very messy. So we looked for a nice alternative. What we came up with was just writing out the Direct3D shader format directly, because actually what you pass to create vertex shader or create pixel shader is a direct translation of what is in the text file. Every word, every 32-bit word in the shader instruction corresponds to 1 token in the text file. So each shader instruction is 32 bits, 4 bytes, and each additional operand is again 32 bits. And also pixel and vertex shaders share the exact same instruction encoding. So the add instruction, for example, is the same in both the binary representation of pixel and vertex shaders. So this is basically a very convenient format to use. There are a few slight differences that not going to talk about here because it's not that important. But just look at how this code looks. We basically have defines for the different instructions, and just this is the instruction opcode, destination register, and the source registers with whistle masks and everything. This is a kind of messy way to write shaders, but still, you can generate it with, you can integrate it in C code, which allowed us, to generate all those shader permutations in Krieger, without having to store 20 or 30 or even more precompiled shader variants. But still, this is obviously not a very nice way to do this, because the code gets messy and hard to read. So we used something different now, or we decided to use something different now. But we still wanted this type of system because it was basically a great success. It makes it very easy to do different variants, because you have just complete C-style flow control to decide which shader variant you can do. Very simple register allocation that basically just has a list of which texture ends up in which register, and that's it. So the second iteration of the code looks like this. It's basically assembled shader code, or with a list of flags, which is just the code or the data or material ops uses. And then you have like for instructions and ifs and indexed access inline in the normal shader assembly code. So you can do, for example, 2 variants of the shader, one with only diffuse elimination, one with diffuse and specular elimination. And you have ifs and everything you want. So this allows you to have those different permutations in a far better to read way than what we had in the C code. And that's what we're using right now, except it hasn't been used in a release production yet. This is all very new, a few weeks old, but we've been able to convert all of our old material code, not just the ones we used in Krieger, but basically everything we've ever done in that direction within a matter of a few days. So, we are optimistic that it's going to work out well.
One last word before I finish this. I'm still looking for 2 programmers at the company I'm working, a PS2 programmer and a gameplay programmer. So if you need a job, just ask me. I might have one for you. Especially for the PS2 programmer, I'm not expecting to find a fully qualified, trained PS2 programmer with 3 AAA tables on its record. We are more talking about educating somebody with the right basic skills into PS2 programming on an existing engine, existing project, just to maintain the code, develop it further, do some more optimizations. I don't have the time for. This is actually the company 49 Games, which was founded by some pretty known seniors, and I think it's an environment pretty well suited for seniors. So after we've filled you with all this stuff, you can ask some questions if it was any use. So
we have 5 more minutes.
5 more minutes. Very good. Ask your questions. And there's one. I already seen it in the F2L section.
Yeah, that's right. I had a question about F2L. I had a similar problem with writing my 4K, and I just used the compiler flag to remove the F2L call.
Oh yeah, the qfist.
Yeah, I use QIFist, or I could also use the SS2 variant.
Why aren't we doing this? We do it? Yeah. Oh.
Is that better than this code, or?
Yeah, it is.
Okay.
Hi. I have a question about the compressor tool. You said you have a table on how many bytes each function uses up, but usually.
No, er soll die Frage schon zu Ende fragen.
Okay. The point is, if you have two functions which has similar code, so the compression routine uses the pattern of one function for compressing the other function as well. How did you calculate the bytes each function would use up? So I think you would not have a compression gain if you change the code for one function and you use the pattern for compression with the second function. How did you manage this in this table, or how did you show this point in this?
Well, this is rather simple. We don't. The basic idea is that mainly in compiler-generated code, you have only very small segments of code that actually match byte by byte. And changing code, you basically always get global changes all around the program. But still, and that is one thing we noticed, what this list does is really just compress the routines, and then the size you get is the size covered by that range of code in the compressed bit stream. So this is only an approximate value, and it changes for all functions every time you recompile, but the differences are usually very small, on the range of plus minus 3 or 5 bits when you're not changing anything related to the function, and usually less than 2 bytes when you do, and not change the actual code. So yes, there is some variance, but we found that the variance is actually small enough to still be able to use this as a very valuable tool.
No more questions? Yeah.
Question? Yeah. So when you're talking about the Microsoft compiler, which version are you now talking about? Is it Visual C++, version 6, .NET 2003, 2005, and what's your experience? Is it getting much better?
We are using 2003, and the code actually got a little bit larger, did it? But it's not all about it got better, but a little bit larger. So I think we can just live with a few bytes more if we get better support for intrinsics. The support for intrinsics got a lot better, and on that it's worth using the latest version. I always feel uncomfortable with using an outdated version. I have the feeling of missing something, and since it is the most important tool for the programmer, it is important to keep up to date. They do a marvelous job, all of these. Intel, Microsoft, and GNU do a marvelous job in creating great compilers. Our needs are a little bit specific because we need aggressive size optimizations when doing intros. But I'm not only talking about intros here. I'm talking about demos or high optimized graphic software in general. I wouldn't use an older version just because of 500 bytes. Yo, if there really is no more questions, I can't imagine that all this stuff was so easy to understand that there are no questions, especially with me presenting it. Then we close it now.
Chaos, thank you. Give him a hand.